right, we are on. We are on camera. Okay.
Live.
So here it is. We are yes. Now we are live. So we are making a truth table for this formula. How do we make a truth table? First, you need to see how many letters you are using. How many letters are we using, or variables? So then that tells you that you need a table with two letters P and Q. How many possible valuations do you have? 4. Each of them has 2 options. So it could be both true or the next one. True, false. Then false, true, then false. I usually like that's called lexicographic ordering. First to keep the first letter true. You see P is true on both, and then Q is changing. Now when I do all the options on Q, then I do the same with P. Are you okay with the start? Now what do we do? If you remember a minute ago, I explained why is this a formula explaining what the building blocks are. Now you need to write all the building blocks. You cannot write formula itself. So who's the first building block? P or Q, doesn't matter. Both answers are correct. So P or Q is there. Then P and Q is there. Who's the next one? Not P and Q. And finally, the whole formula, just call it F. I don't want to copy, but I know that I use N between them. Is everybody okay with this? So what do I do once again? I wrote both variables. I wrote all the valuations, and I wrote all the building blocks. By the way, maybe to connect it with the end of our course, again, I didn't mention that in the notes. Every formula has its building tree. So actually, I'm writing all the nodes of the building tree, if you want to write this, because this is like pushed building tree. What is the building tree here? Here's P. Here's Q. Here's P. Here's Q. By the way, this is a very important way how you build mathematical expressions, even in calculus. What do I do with the first P and Q? What do I do in between? 4. Second one N. Then I do neg. And then between those two, what do I do? N. Here is a tree that explains the structure of our expression. Every expression has a structure. And trees are much better to express mathematical facts than one line. And, you know, half of the students in nation in like 5th, 6th grade struggle because math expressions are in one line, and to understand parentheses and those PEMDAS rules because they don't see the tree. Actually, to see from the line, to see the tree is a big deal. And generally, so if you have, do you understand how I made the tree? So P or Q is the first building block, P and Q is the second building block. Then you negate that, and you put N between that. And if you look at the tree and those columns, every column represents one node from the tree. Do you see that? And then what do I do? Now it's just, you know, simple arithmetic. So P and Q, if I have P or Q, what do I do? Is it always true except in one line? Agree? True, true, true. The only time when it's false is when? When they are false. What about P and Q? True on top and then false on all the other. But then what do I do? I negate the previous line, so I'll switch all of them to the opposite. False, true, true, true. And then what do I do? I take this one and this line, and I will do conjunction. So true and false is what? True and true is what? True and true? False and true? Here it is. So what did I do here? Here I told you for all the possible valuations, what will be the value of this formula? Is that clear? So I told you when will it be true, when it will be false. There is one more thing that I achieved here. I established that actually really this has the same meaning as P or Q. Why? I can write on this side P or Q. And what did we say? P or Q, when both true, that's false. When both false, it's valuation? For logic, when two formulas agree on every valuation, we treat them all as the same formula, at least the same meaning, although maybe not the same form, not the same building procedure, but like, you know, x squared minus 1 and x minus 1, x plus 1. Is that the same expression or not the same expression? It's not the same expression. Why? Because for this one, I need 4 symbols, and for this one, I need 10 symbols. Do you agree? It's not the same expression. Don't be that easy on accepting something as the same. But do they have the same value all the time? Yes or no? Yes. So they are tradable for one another, even if not being the same. For calculation purposes, they are the same. Do you agree? And so the same thing here. This and this, one might argue that they are not the same building procedures, but do they have the same value all the time? And those formulas are tradable for one another. Is that clear? There's also certain formulas get true on every valuation. Those are formulas that are always true, and those formulas have a special name. They are called tautologies. So tautologies are formulas that are always true, and they are important for the laws of thinking. We'll talk about it more next week. So tautologies, or those that are always false, we call them contradictions. Is that clear? So, you know, I'm introducing some terminology besides the reasoning. So, let me skip a few things here. Oh, I did it the same thing as my notes. I forgot that I did it. So here it is, exact the truth table. That's the same example there. It says here, just I'm not going to write it on the board. P or not P. So P or not P is a tautology. If I ask you to do that question, what are you going to do? Take a table, and that's only one letter. How many lines do we have? 1. 2 lines. One variable, true or false. In both of them, did I get true at the end? Yes or no? And then, so that formula is tautology. By the way, that tautology is very important for the law of thinking called what? It's called principle of exclusion of the third. You are either true or false. There is no third case, and that's very important from the time of Aristotle, at least, or even further on. Very important law of thinking. It's called exclusion of the third. Unfortunately, people in the beginning of 20th century relativized that and said, well, maybe that's not true. And that's what you can find in branch of logic called intuitionistic logic. They say you cannot use that principle that if you exclude not P, then P must be the only remaining case. You always have to prove things on their own. And it makes somewhat sense what they say. All right. Here I will just comment. I don't think that there is a big reason here to just write it on the board. Let's see if this follows the same logic. It's called De Morgan's Law. By the way, De Morgan's Law is one of the most important laws that we'll use in our class. It's like, you know, like we have commutative law and distributive law in algebra. Remember those? So here we have De Morgan's Law as a very important law. What is that law saying? Actually, it's saying this. When you negate P or Q, that's the same as negation of P and the negation of Q. This time, I'm not going to ask you if you agree with this or not. I will just write a table and I'll be done. You understand? Politics is done in the first 10 minutes. Now we do things according to the rules. So first let's establish it. So I did P and Q. P or Q, is that a building block, yes or no? Not P and not Q are building blocks. Then if I have P or Q, I can have negation of P or Q, and then conjunction of those. On every line I did calculation. I'm not going to do calculation in front of you. That's easy. Look at those. I got F, 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 T. What about this one? Do they have the same value for every valuation? Are they equivalent? Are they tradable for one another? Like this. Actually, like this is tradable for this. However, you need it in algebra the same way De Morgan's Law tells you, and De Morgan's law is important. I'm going to go there. Camera cannot see us. What? The Morgan law, you can think of it, although I don't like you to think of it that way. But people often think of it this way. Negation of P of Q. Like negation gets into the parentheses and attacks them individually. And what happens? Negation of P, negation of Q, but what's important? It's going to be end anymore. It will be what? Or. The other, or, I didn't have that one on the board. I have the other one. Both of them are okay. So negation attacks disjunction and makes what? Goes individual and then makes conjunction. And kind of it makes sense. Because what? Even without tables, you can argue in common sense. Because if someone says that disjunction is not true, what is he saying? That they are both failing, don't you agree? First one is failing and second one is failing. And that's why disjunction is not. So this is called De Morgan's law, from one of the first logicians, De Morgan. Here's one example. Where is that useful? Although I'm a little bit mixing in here predicate calculus, but doesn't matter. I hope you won't be confused. So we want the following. It says, write a negation, so statement field, although this is predicate calculus because there are letters. There are variables and relations. Here's a statement. Someone says, solution of this equation is between -2 and 7. Okay? And you are negating that. You say, no, that's not true. So you say, phi is not true. What are you really saying? So here it is. What this says, what does it mean that x is between -2 and 7? That means that x is what? Greater than or equal to -2, and at the same time, x is less than 7, agree? So being between -2 and 7 means you are right from here, and at the same time you are left from there. So interval is always empty. So when you do negation, so if I call this P and this Q, what are you saying? You are negating P and Q, which is equivalent, according to De Morgan's law, to what?
Not P or not Q.
Not P or not Q. Which is equivalent to what? And not P, you are saying it's not true that the number is greater than or equal to -2, or it's not true that x is less than 7. So what you are saying is that x is what? Less than -2, or x is what? Greater than or equal to 7. And if you remember, it makes sense, because if this is -2 and this is 7, if you are negating, you are saying that you are either here, what? Or here, and that's exactly what we said. All the remaining pieces are those in, they belong, can they belong to both of them? Of course not. You cannot be at the same time, younger than 20 and older than 60. So, you can be between, but never can. You might be or. Any other question or comment? Okay. All right. So, here's one illustration. Why it's so important? When do we use these laws, even if we are not aware of it? You have a regular algebra class, they ask you to do this all the time. As I said, of course you can say, I knew it even before I took discrete math, but now you are automatizing this procedure so that you can do it safely and accurately. What else? Here is the list of some tautologies or equivalences between the formulas that actually tell you that you can use them all the time in your logic. Because there are equivalences here, but among the sentences, they justify correctness of the sentences. So what is that telling you? First one, this is commutative law, it's sort of for logic. It says, if I say P and Q, that is equally true as Q and P, do you agree? So you can reverse the order of two components. How would you call the second one? Is it the associative law? So, and it is true for what? It is true for and, but the same way it is true for or as well. And then here is for or. Same thing for and for or. What about this one? Line number 5 might be interesting. What is that? Distributive law. But how is it distributive? Be careful. Among the numbers, 2 times x plus y, is that equal 2 times x plus 2 times y? Yes or no? So times, if it's outside, it can come up in the parentheses and then attack the pieces, do you agree? But what if it's plus outside? Can plus attack and have distributive law? No, you have just half of the distributive law in algebra. What about here? We have both of them. All the laws are symmetric. Whatever and can do to or can do the same thing to and. So that's, we have the formula. So here it is. Who's outside? And usually we think of and as multiplication, but we should not completely. So and then attacks both of them individually, which is P and Q, P and R, and plus in between them. But also what? If it's or outside, can it also work, yes or no? Yeah, so if it's or outside, it can attack individually, and then and comes outside. What about this one? Double negation. If you know, as I said, I'm not going to argue on this. Make a table and you will see that they have the same table. What about this one? Exclusion of the third, it's always true. What about this one? This is De Morgan's law that we just mentioned. It's listed. Negation outside comes inside and switches and to or. What about this one? Same one, but negation attacking or and making it and. What about this one? It's called absorption. What is that saying? Look at this. Who's there? P, P, and Q. Is one of them repeating? Yes or no? Yes. And that one is repeating. It comes inside and then outside. And then what? One is and, one is what? Or. When that happens, what do? Just that repeating one appears, everything else disappears. Can you do another version of absorption by duality? What would that be? P, then what? Or what? P and Q is equivalent to what? P. No, P, whoever's repeating. Doesn't matter P or Q. Repeating one appears. That's called absorption law. And you make a table and that's what you do. So, all right, so, quick comment. Which of the following statements are propositions? Help me if you can. No, this half of the lyric might be. What? Emperor Constantine was born in Niš.
Yes.
Is it true, by the way?
No.
Yeah, yes, it is. Yes, it is. Yes. But he was raised in Trier, I think. Yes. So. All right. What about C? Niš is the town that I come from, so that's why I'm so happy about it. What about 3 plus 2 equals 7? Is it a statement?
Yes.
Yes. I'm not asking is it true or false. Does it make sense to say true or false? Where is the road to Dover? No. Do you know where is this quote? No. I don't know. No, there is a movie by Richard Lester with Beatles again, and there is a, and which one is that? Oh, it was a long time ago. Where there's a character that every like 20 minutes shows up a guy completely confused and tells me who knows what, and he comes, where is road to Dover? And you know, I kind of, he doesn't care about anything else but that. So this is not a statement. I believe that you know which way is the road to Dover. This is a statement. It makes sense. I believe or I don't. So that makes sense. And then x minus 3 plus 5. In Ebb's book, she would say no. It's not a statement because you cannot say without knowing it. I disagree. I think that this is a statement. Why? It makes sense, of course, when someone specifies x. If you tell me x, so I would say that this is a statement. You know. But you see, sometimes things are, you know, a little ambiguous because definition is not precise, and that's why sometimes things could be answered one way or the other. Yeah.
Would you say that this is
cannot say it's true and false because X is ambiguous. So you know, with changing X, the whole thing changes the value. But doesn't
So you
matter.
could have a true statement or a false statement depending on.
Exactly, but doesn't matter. I'm not saying, you know, it does make sense. What if I think of X as being actually fixed but hidden? It's just X is 7, but no one told me that. You know, then it makes sense. So very often I think of this expression that, so it doesn't matter, it doesn't hurt you saying yes or no, as long as you develop intuition, what makes sense to call a statement. So that's why I put an ambiguous one at the end. All right, questions, comments? Yes.
Is the first quiz going to be true, false, like that?
Your first quiz will, I think, be on Monday, and that one will be to make a table and to check if formula is true or not. I'll tell you more about that. All right. Necessary and sufficient presentation. So it's fairly easy, but just can we check it on the way out? Because people are coming. I think